Okay, I guess the fourth time's charm. I actually tried this 3 more other times. Well, that would be 4, wouldn't it? Trying to put together a video, and I think I just was trying for too much. It kind of got away from me. So here we go. I'm going to make several smaller videos out of this, but this is really just what we did in class the other day, but I wanted to put it down in video. So we have the velocity analysis at any point in a linkage, and this is the example, which is a modified example here where we're going to use 75 degrees instead of 40. And sorry for the background noise. I don't know if you probably kind of annoying. That's the 3D printer. We're making face shields, and so it's running nonstop now, so it's going to be on a lot. So what we've done is I've modified the position of the thing, and I also changed, well, I added from the original example, I added this extension onto the coupler for the previous video in which I modified the full rotation and demonstrated that. And then I made a velocity also, right? So we could find so we could have a point that would be of interest to us, P. But now I've changed this to 150 millimeters, and I've changed this angle right here, just so that I could get sort of a more interesting curve. And then so my goal is to find the velocity of point P at that. At this configuration, at the theta 2, when it's omega 2 is 25 radians per second. In another video, I will do the Excel, MATLAB, and SolidWorks, and maybe I think I'll do the Excel one here, but I will do the I'll do the rest of the MATLAB and SolidWorks in a separate one, just because I kept messing things up, and it ended up when I tried to trim out the bad parts, it kept crashing on me, and so that's what I'm doing here. So I assume I'm going to do a position analysis at that 75 degrees, and so I'm able to do that with spreadsheets that I've created or other tools to be able to find that theta 3 and theta 4. We know that that's probably the most difficult part of doing any of these 4 bars is having to solve for that theta 3 and that theta 4. And then we do a velocity analysis, but we should spell it correctly. When we do a velocity analysis at 25 radians per second, we're able to get the omega 3 and the omega 4. And we really just plug and chug most of the time for these. But I think I did in the other video, I might have demonstrated that we could also get these numerically by way after we've done a position analysis for full 360. And I'm going to need the velocity at point A, and I get it from using this method. We could just as easily have gotten that by hand, because it's just going to be our 40 millimeters times our 25 radians per second, and then just put it into an angle. But I went ahead and did it this way right here, just to keep this in mind. And then so we get with those velocity hours with the components. We don't actually need the velocity of B or the velocity of B with respect to A. I just put those there for just to keep on with that idea, right? That this was the big idea in our velocity analysis. But now we want to extend it, and we want to find this point P. By the way, I think there's an error right here. I switched those two things back and forth, so. Just to let you know that, I mean, we're not going to use it, so it doesn't matter. So if I want to find the velocity of P, I take the velocity of A and I add the relative velocity, P with respect to A. And I can find P with respect to A in a very similar way to what I've been doing. I just take the magnitude of AP right here and multiply it by omega 3, because this is one piece, right? This is one rigid body right here. And so because the coupler link right here that we think kind of that of being the link is moving at omega 3, that the entire thing, this is just a rigid body, is moving at theta 3. And oh yeah, I should multiply by J and then multiply by E raised to the J. And now the angle of this piece is going to be theta 3 plus del. right? So it's going to be this entire angle right there from horizontal. And theta 3 plus del is going to be, what is that? Where did I find out from my position analysis, right? It was 18.25 plus my 15. So that's a 33.25. I can do that math. So I stick in these numbers. AP is 150 millimeters. I found for my velocity analysis that omega was 0.4842. And then I took the Euler identity, but with already multiplied by j, so the sign is negative and is the real number. And here we got the j and then the cosine of the 33.25, and I end up with a negative 39.82 plus j times 60.74 millimeters per second. And now if I want VP, all I have to do is add the two components right here. So I will take that negative 965.9 and add my negative 39.82. And then I will also take my 258.8 and I will add my 60.74. And what I end up getting is a negative 1006 plus j 319.5 millimeters per second. So that's the velocity of P at this configuration right here, right? And I believe we found that everybody was rotating to counterclockwise, right? So omega right here, 3 was this way right here, and omega 2 is that way right here. So we're really looking at that right there, right? This is the VP. And you can see that it's tangent to the path, because that's the thing we want to always remember. Now, we want to do this in Excel. We want to check this in Excel. We want to check this in Excel, MATLAB, and SolidWorks. We want to confirm these values. So I'm going to keep this, and I'm going to rotate my screen. So give me a second here. Detach that. And let's see, which one am I going to go? I think I want to go to this right here. Okay, so this was the position analysis one, and how far did we go? Well, this was for the 360. Yeah, I think I want to go to the 4-bar analysis right here. I think this is the one that we left off with. Yes, I believe so. And I'm going to make a copy of this, and you can see that I've already made copies of it before. Right, so this is the one that we're working on right here. And 4-bar velocity 3. I should have moved that over to here. Okay. And I've already was checking something up above, so I modified it slightly, but we were able to find for our, okay, so let's modify for our conditions here. It was 150 in this problem. Theta 2 we decided was going to be 75, and this del was 15, and I think everybody else is the same. So if we were to take a look at our answer here, we find for VP, remember, all right, so and take a look at the chart of the thing, and sure enough, it looks like this. We're going to find that we have negative 104, negative 1004, and 318 0.4, right? And so if we want to, let's just paste this in here so we can just look at them side by side. Here is the Excel answer versus our by hand, and you can see that we got this, that's darn close, right? And we can improve upon that, of course, by making our increments better, right? Right here we had a 5, I can go 2.5. And then I have to scroll down because 75 is now moved over to here. And we can see that we got negative 1005.3. And I'm just going to paste this back over into here and take a look at it. And yeah, sure enough, look, check it out. Yeah, we got closer to what we had before, what we had by hand. And then, of course, we could just keep going if we wanted to. I'll just do one more, 1.25 increments, and we can scroll down and find 75 right here, and we look over to there, and we get pretty much right on there. Paste the picture. So there you go. We have pretty much demonstrated that we could get the velocity analysis using Excel, and this is convenient because now this is like a tool that we could use for other 4-bar problems or other and coupler curves and that type of thing. So that's useful to us. Now we want to. Yeah, I think right here is where I'm going to break off and then do another video. So we'll be picking up at the next video. Let's see what this is. 11 minutes. That's not too bad. So all right. So I think I can record myself this way. I'm wearing my Dunder Mifflin shirt on right here, and we're drinking our. I like it's weird. It's always put this little thing. It wants to find my face. That's nice of it.